Hello, and welcome to Behind the Scenes, where we take a closer look and a deeper dive into our lecture material. And let's go ahead and talk about sections 3.3 and 3.4. We're talking about the eigenvalue eigenvector systems that coincide with the first order differential equation x prime equals a times x. Now, very similar to our working with our characteristic equation, just now introducing the concept of eigenvalues and eigenvectors. We still talk about these in a very similar fashion. However, I think once we get away from distinct real eigenvalues, it starts to look a little kind of different. And I want to talk about why that is. So let's go ahead and start with the case of repeated eigenvalue. So repeated eigenvalue lambda. And we would start by saying, okay, well, I should get two solutions from this. It should be x sub 1 is my eigenvector. I can call it v sub 1 times e to the lambda t power. But then if we're thinking about the characteristic equation and how we solved back then, we're thinking, well, okay, well, what about then x2 is equal to, I have e to the lambda t, since that repeats. And then if I use that same eigenvalue, it's going to give me the same eigenvector, so I got v1. And then, so what do we fix? We just multiply by t, right? So this should still be a solution if I'm thinking about the characteristic equation and solving like what we did with the homogeneous differential equations back in section 2.3. But under further investigation, this is not a solution to x prime equals ax. And let's show that. If it is a solution, so we'll go ahead and we'll say that x sub 1 is a solution. But I want to know if this is also a solution. Well, let's see. So I have x sub 2 here. Let's find the derivative, x sub 2 prime. So I can rewrite v1t, and the derivative of e to the lambda t is e to the lambda t times lambda. And then I can add to this. Now I can rewrite e to the lambda t, and the derivative of v1 times t is v1, and that's my derivative. And I want to check that x2 prime is equal to a times x2. Is this true? Well, let's see. So x2 prime, let me actually just rewrite this underneath, and I'll maybe try to make it look a little bit neater. We'll say v1 lambda t e to the lambda t plus v1 e to the lambda t. I want to know, is this equal to a times x2? And x2 was my, pretty natural guess coming from the characteristic equation of a times v1t e to the lambda t. And I think this starts off looking okay. If I set my like pieces equal, I have on the right-hand side, the only term involves t e to the lambda t. And on the left side, I have a term involving t e to the lambda t. So setting those two parts equal, this means a v1t e to the lambda t must be equal to v1 lambda t e to the lambda t. And I'm not trying to make any restrictions on my function of t. I'm not trying to make any restrictions on e to the lambda t, although that will always be non-zero. I can divide both sides by that and say, well, really what this means is that a v1 should be equal to lambda times v1. So sort of ignoring that they both have t e to the lambda t on each side, or thinking about just omitting those. So this means a v1 is equal to lambda v1. And this is true. This is fine. This is fine. This is just saying what we already knew, which was that x1 is a solution, and giving us that eigenvalue eigenvector relationship, that av1 minus lambda v1 is equal to the 0 vector, or then factoring out v1, that a minus lambda I times vector v1 is equal to the 0 vector. This is true. This is correct. That's fine. I have nothing bad to say about that. But that's not it. That's not the only stuff we have. We also have this lone term that does not have a t in it, and it doesn't really have a like term on the other side. That would just be, for example, if I wrote in plus the 0 vector. But this is a big problem, because if I set those parts equal, over here on the left I have that remaining piece, v1 e to the lambda t. On the right, I don't really have anything, so then it has to mean that it's equal to the 0 vector. This is going to spell bad news for us, because the exponential term isn't going to be 0. That means all of the responsibility falls onto the vector, that the only way this can be true, realistically, is if v1 is equal to the 0 vector. No, I don't know if you can tell, that's not even a sad face, that's an angry face. That's not good, because we already said that v1 is our eigenvector associated with our first piece of our solution, x1. An eigenvector must be non-trivial. So we say, but v1 is a non-trivial eigenvector. So v1 cannot be equal to the 0 vector. This is a contradiction, which means that this x2, although we did everything we were supposed to, everything expected of us, that we went and thought about the characteristic equation and just applied that idea now to our eigenvector eigenvalue systems, this is not a solution. It's not going to work. Well, okay, what is our other solution then? Well, we don't give up in differential equations, of course not. We just try to be creative and hope that we get lucky. So we still have a solution, x1 is v1 e to the lambda t. What if our other solution, x2, isn't too far away from this? So although I didn't get what I wanted off of my first guess, I still have this feeling that I'm not going to have to venture too far away from that original guess to get something that's going to work. So we'll say, well, what about if x2 is equal to, and I'm going to keep this, I'm going to say, what if it's v1t e to the lambda t? But then what if I need another piece to it? What if the other piece still has e to the lambda t, since it should? I'm not trying to get rid of my exponential function. But then what if it's just another e to the lambda t times just maybe some other vector? Maybe some other vector. And maybe it won't work. Maybe I'm just here wasting my time. But if it's going to work, then I'll probably be able to see under what conditions it will work. So this is going to be our second guess. And we try some things. If it doesn't work, it doesn't work. But let's be optimistic at least. So here, let me jot this down on this next page. We're saying, well, what if x2, our other solution, since x1 is already a solution, v1 e to the lambda t. Well, what if x2 is that v1t e to the lambda t that we would initially guess, but then plus just some other vector v2 times e to the lambda t. Is this going to work? And I don't know, so let's find out. So we're trying to see if this is going to satisfy that x prime is equal to ax, or in this case that x2 prime is equal to ax2 for our new guess. Now let's find x2's derivative. First, a bit of a product rule and chain rule. We would say here v1t comes along, derivative of e to the lambda t is e to the lambda t times lambda. We add to this, and still looking at this first term, now I can rewrite e to the lambda t. Derivative of v1t gives me v1 with respect to t. But I have one more term, so here I have to differentiate this on its own. So v2, and then the derivative of e to the lambda t gives me e to the lambda t times lambda. And I want to know, is this going to satisfy that x2 prime is equal to a times x2? Well, let me write this over again. So v1t e to the lambda t. Let me get that lambda, let me move the lambda in. v1 lambda t e to the lambda t plus v1 e to the lambda t plus v2 lambda e to the lambda t. I want to know if this is equal to a times x2. So imagine multiplying our original guess x2 by a, distribute that matrix in on the left-hand side. So that would be a v1t e to the lambda t plus a v2 e to the lambda t. And let's go and set those like pieces equal again like we did before. So on both sides, I have a term that involves t and e to the lambda t. So we can sort of showcase that. And so those two pieces should be equal, meaning that a v1t e to the lambda t is equal to v1 lambda t e to the lambda t. And remember, we're not trying to make any restriction on t or e to the lambda t. So we can just divide by e to the lambda t and ignore t. Really what we're left with here is saying that a times v1 is equal to lambda times v1. And this is good, this is fine, this is true. This is just saying, like what we said before, that x1 is a solution. Just like we said earlier, I can subtract this over and say a v1 minus lambda v1 is equal to the 0 vector, and factoring v1 out, that a minus lambda I times vector v1 is equal to the 0 vector. I have nothing to say about this, nothing bad to say about this. This is great. I already knew it. That's true. Thank you for telling me again. Thank you for reminding me. But then that means that all my stuff that's just e to the lambda t times, vectors, matrices, lambda as a scalar, that all of these things must be equal. So this means that my AV2 e to the lambda t should be equal to v1 e to the lambda t plus v2 lambda e to the lambda t. And let's get the v2 terms on the same side. So we have AV2 e to the lambda t, and then I can subtract that last term over. We'll say minus v2 lambda e to the lambda t equals v1 e to the lambda t. Now e to the lambda t is some exponential term. It'll never be 0, so it is some non-zero factor here, and I can divide both sides by it so that we get AV2 minus v2 times lambda, but let me write that as lambda times v2 equals v1. And here on the left-hand side, if I want to factor v2 out, we have a minus lambda I times vector v2 is equal to vector v1. This isn't a bad statement. I don't feel anything negative about this. Remember last time I drew the frowny face. I drew the frowny face because I got the result that my non-trivial eigenvector that is not ever supposed to be the 0 vector has to be the 0 vector. And I said that's an impossibility, that's a contradiction. But what I'm getting here, it's not a false statement. It seems kind of cryptic at first glance, but what it actually is then is it's a suggestion. It's trying to guide me. This is a suggestion that I'm getting. It's saying, hey, I'm not going to tell you no, it's not going to work. I'm not going to tell you that your second guess was wrong. I'm going to actually try to help you and tell you that it'll work. It'll work provided a minus lambda I times that new vector v2 is equal to vector v1. If that's true, then you're good to go. Something interesting to notice about this, let me rewrite it underneath. A minus lambda I times vector v2 equals, leave some space, times vector v1. If I multiply both sides of this equation on the left by a minus lambda I, which is just some matrix, so let me multiply by it again, I'm able to say something interesting here. Because now if I look on the right-hand side, I have a minus lambda I times vector v1, but I know that that's equal to the 0 vector. So then looking at the far left and the far right-hand side, and over here on the left I could say this is a minus lambda I squared. So a minus lambda I squared times vector v2 is equal to the 0 vector. And this gives me two things to consider when choosing this new guess. So this means our new guess is actually okay. It can work, right? We can work with this. This could be doable. A little smiley face. Happy now. However, how do we choose this vector v2? Well, it has to be such that these two conditions are satisfied. So looking at this a bit more closely, what has to be true Well, I have to have that a minus lambda I squared times this vector v2 generates the 0 vector, and also that a minus lambda I times vector v2 is equal to vector v1. This first condition, which I actually solved for second, but I wrote it first, this is something I want to talk about a bit. A minus lambda I squared is just some matrix. So this says a matrix times a vector has to give you the 0 vector. I want this vector, of course, v2, to be non-trivial. If v2 is the 0 vector, then I've actually not introduced anything new into my second guess. This was my old guess. This is something new to it for my second guess. So this better not be the 0 vector, or else I'm back to square one, which I already know failed. So we're saying, okay, so then thinking about this, I want to see what condition this really places on this vector v2. And certainly, a matrix times a vector can give you the 0 vector, and neither of those two pieces as a factor have to be the 0 matrix or the 0 vector necessarily. These could have non-zero entries and could still work out to give you the 0 vector as a result. What's interesting is that we can show for our examples that a minus lambda I squared is the 0 matrix. Or let me actually rephrase this. I mean, we can show it, but we should. We should show that a minus lambda I squared is the 0 matrix. If that's the case, then the 0 matrix times v2 will give me the 0 vector no matter what v2 is. So what this means is if I can show, and I should show that, if I can show that a minus lambda I squared is the 0 matrix, this means then v2 can be any vector such that that second condition is still satisfied. A minus lambda I times vector v2 is equal to v1. So this actually narrows down what we're looking for into just one condition. We're saying I need these two things to be true. If I can go through some extra work to show that a minus lambda I squared is the 0 matrix, then this first condition will be true no matter what vector v2 is. It'll always be true, sort of vacuously true, and that's a good situation to be in because now we just have to look at the second condition. So that's why when we're approaching these problems, we're doing the steps that we're doing. We're saying, let me show that a minus lambda I squared is in fact the 0 matrix, which means with this first restriction that there's actually nothing to say. v2 can be any vector. I do want it to be non-trivial, which then just narrows down my search to making sure that that new vector v2 fits this second equation perfectly. It has to be exact, that a minus lambda I times vector v2 is equal to v1. No scaled versions here. It has to be precisely equal, but as long as I can show what we talked about for the first condition, I can then work with the second condition to build this vector v2, and then I can build my second piece to my solution, v1t e to the lambda t plus v2 e to the lambda t. And then I can start introducing, coefficients, etc., etc. But so hopefully that cleared up the idea of the repeated eigenvalues. Now, I want to talk very briefly about the complex conjugate eigenvalues. There's nothing really overly remarkable to say here, but if my eigenvalues give me this complex conjugate pair, a plus or minus bi, then we can sort of talk a little bit more in depth about the steps that we were taking in this case. And this involved quite a bit of work, but there were some shortcuts we could take. I want to start off, though, by mentioning something very interesting. A lot of the results and a lot of the shortcuts we take stem from linear algebra. We don't really have enough time in the semester to turn our differential equations course into a full-on linear algebra course, but let me at least give you some ideas. If I have a times v is equal to lambda v, what we can do is we can take, if these two things are equal, we can take complex conjugates of each side. And the notation for a complex conjugate is just the bar over top. So we can say then AV bar is equal to lambda V bar. If these two things are equal, then their complex conjugates should be equal. And what we can say further is that the complex conjugate of a product is equal to the complex conjugates of the factors multiplied. So we could say this is A bar times V bar equals lambda var times V bar. And furthermore, since A is a real matrix, the matrices that we looked at, those 2x2 matrices, only had real entries. So the complex conjugate of that real matrix, there were no complex parts to it, so I didn't have to worry about any of that, which means that the complex conjugate of a real valued matrix is just that same matrix. That there's no complex part that I'd have to flip the sign on or anything like that. But this is an interesting result. So this says if V is an eigenvector corresponding to, let's say, lambda equals A plus BI, then a direct result from this that we've showed, and here's how this is, how the proof looks. It looks really cool. It's very interesting. It's not as wordy as some of my usual proofs. Then we can show that if I take the complex conjugate of lambda, which is lambda bar, which is A minus BI, the complex conjugate, this also is an eigenvalue and has an eigenvector V bar, which is just the complex conjugate of V. So we're saying if I have these complex conjugate pairs of eigenvalues, then if V is an eigenvector corresponding to one of them, the complex conjugate of that eigenvector corresponds to the other eigenvalue. However, none of this is even stuff we work with. That's actually quite remarkable, that what we can show is that since our eigenvector is complex, or let me be sort of specific here, we'll say has real and complex parts, we already have two vectors. So sort of the idea here colloquially is that if I build just one of these eigenvectors, I don't need to find the other eigenvector because working with the real and complex parts from one eigenvector actually gives me two vectors to work with, and those two vectors can serve the role just coming from one. So it's sort of, you get, more for your money in this case. We get one eigenvector. It's not so great because we got real parts and complex parts, but it doesn't want to ruin our lives. So as a consolation, it now serves the role of two vectors for us to work with. So let's say that we just find one of these eigenvectors V. We can think about it by splitting it up into the real part, call it P, plus the imaginary part, call it Q, times I, since it's the imaginary part. So if I split my eigenvector V into a real and imaginary part, then I really get to work with these two pieces. But I know what you're saying. You're saying, oh, there's so much work beyond that. So don't even try to kid us into thinking that we're done at this stage. Well, no, but let's try to make some sense of what happens next. So we already had our eigenvalues. That was lambda equals A plus or minus BI. And let's just assume without a loss of generality that this vector that we have, and this isn't bar, this is a vector hat notation, this vector V has a real part of a vector plus an imaginary part of a vector, and that came from the eigenvalue A plus BI. Then what we would say is we'd say, okay, so we have, still thinking about the characteristic equation, we have e to the power of A plus BI times t times my vector v. But here my vector v, I'm going to split this into p plus qi. And let me sort of ditch the vector hat notation. You know these are vectors. I already said they're vectors. I can split this up even further and say, well, this is equal to e to the at times e to the bit, or let me write that as bti, times p plus qi quantity. And then we remember from our discussion with the characteristic equation that I would use Euler's identity on this e to the bti. So e to the at just sits out in front. It's just chilling. It's not doing anything. But then here, e to the bti, expanding with Euler's identity, gives us cosine bt plus I sine bt. And it's that times p plus qi. But I think it's pretty straightforward that this is not where we stop. We're not done here. And a lot of times you'd say, well, why can't I just, work with my vector and take that real and that imaginary part? Or why can't I look at what I have here and say, well, I want this piece, or I want that piece, or this piece here. This is a product. I can't just start dissecting a product. These two things rightfully should be multiplied, and they should be FOILed out. So when you think about it, or sort of take a step back, it's kind of a wild accusation to say that at any stage, when we still have this product left over, that we should be able to just start dissecting it and taking separate pieces of it. No, that's not at all okay. I want to do the right thing, the appropriate thing, which is to FOIL this out, to multiply it. So we multiply it. And e to the at can just stay factored all the way in front, just like we like to do. But for multiplying this out, we FOIL, and we're going to get a real part and an imaginary part. The real part, I'm going to get cosine bt times vector p, so p cosine bt. And then also another real part is going to come from I sine bt times qi, because it's going to give us I squared. I squared is -1, so we get negative q times sine bt. And that's all the real stuff. Plus, and then I'm going to get the imaginary stuff that's multiplied by I. And that's going to be the cosine bt times q times I. So we'll say, well, that's going to be q times cosine bt. And then that's going to be the I sine bt times p. And we factor the I out, so we have p times sine bt. Now that this is multiplied out, and e to the at always just sort of sits there patiently in front, since it's something that can stay factored out, we leave it factored out. Now is when it's safe for me to go and say, okay, now I can start making my demands. I want the real part, I want the imaginary part. Those are going to be the two pieces to extract. So we'd say, well, now I can think about this in terms of these two separate pieces. E to the at times the real part, where here the real part is this p cosine bt, remember p is a vector, minus q sine bt, remember q is a vector. And then the other piece that I want to work with can be the imaginary piece, which is e to the at, is still there, of course, but then times, now I have q cosine bt, where q is a vector, and then plus p times sine of bt, where p is a vector. So now is where I get to sort of extract the real and the imaginary parts and say, oh, this is what I want. This is what I'm going to use to build my solution. But really, I have to go through the necessary steps, which is thinking about e to the lambda t, plugging in my complex eigenvalue, multiplying by the eigenvector, and here the vector gets split up into the real and the imaginary pieces. Then using Euler's identity, I have to go through this. I have to generate it from scratch, use Euler's identity, and now I can't just pick random pieces of it. That's very dishonest. We don't want to do that. That's way too sort of haphazard. So I need to expand this out. Once I expand it out, now it's no longer really a product. It is multiplying e to the at, but it kind of always is. Now I look at what's happening aside from that, and I say, well, this is now a sum. And of the sum, I can extract the real part, the imaginary part, and from those two parts, I can build my solutions, the individual pieces to make up the solution. Anyways, that's sort of my colloquial take on it all. Hopefully this makes sense. Hopefully it gave you a little bit more closure when it comes time to thinking about repeated eigenvalues of multiplicity 2, and when we talk about those complex conjugate pairs as eigenvalues. Thank you so much for taking a look at this behind the scenes look into our material. I'll see you again for some more lecture material, so take care.